Hi everyone. In this video, I'm going to discuss about insertion sort technique in design analysis of algorithm. So this algorithm we are going to discuss under the concept of decrease and conquer. So this is one of the example of decrease and conquer method. Before you are going to take an explanation of this algorithm, so first of all, we'll see what is the logic is behind for sorting an elements in ascending order using insertion sort. So in insertion sort, we are not doing any swapping operations internally. So simply we are going to performing an insertion operation, right? So before I'm going to solve this particular problem, I try to give an explanation about this algorithm. So try to understand this, then we are going to solve this problem step by step. So now this is an algorithm for insertion sort. So here we can take an array of elements. So now your array will consisting of n elements. Array index always starts from 0, so that the last element it can be taken at the position n minus 1. So now you can take an array of size n. So which index can be taken from a of 0 to n minus 1. So now these three are the comments. So see what these comments will say. You can sort the given array by insertion sort. So this is about your program. So what will be your input? So your input it will be array of size n and your array name is A. So that the indexes differ from 0 to n minus 1. So of n orderable elements. So now your array elements are not in order. So what is your output? So now you can arrange all the elements in non-decreasing order. So simply non-decreasing order is nothing but increasing order, that is ascending order. Okay, so that is your output. So now this is your algorithm. So see, this is your for loop, right? So your for loop is going to be run from 1 to n minus 1. So here array of size n. So suppose if your array size is 10, so now your n equals to 10. But your I is run only from 1 to 9 only. So when your n is 10, your n minus 1 is 9. And your array index is referred from 0 to 9. So every time you are taking the I value, it starts from 1 and it ends with 9 only. Okay, so remember this before you are going to proceed with your algorithm. And then you can take one variable, right? You can take one variable v and you are going to assign every time the a of I position value. So suppose for example this for loop will say I value is 1 initial, right? So now in this iteration your v is going to be assigned with the a of 1 position element. Okay, and after that your j is always takes a value starting from I minus 1 position. So that is, see, your I is 1, then your j is becomes to 0. Your I is 2, then your j is becomes to 1. Right? If I is 3, then your j is 2. So like that your j value is going to be take. Okay. So after that we have a while loop. So while is nothing but an entry control loop. So simply your while is entry control loop. So now this loop will decide when you entered into the loop. So here this is a condition. So what is the condition given? So j is always greater than or equals to 0 and a of j position means whatever the j value in that position element is always greater than v. So what is this v? V is having always the a of I position element. So if this condition is true, so then only these two statements is going to be executed. That is a of j plus 1 tends to a of j. So that is what is the meaning of this. Your a of j plus 1 position element. Now it is assigned with a of j position element. And then you can decrement your j value by 1. Right. So you can do these two steps. Okay. So else if condition fail. Right. So what we can do? You can do this step. So that is a of j plus 1 tends to v. So either you can insert the j plus 1 position element with a of j, or else you can insert a of j plus 1 position with I. So these two are the things it is going to be happen. So when this will happen and when this will happen, if this condition is true, So then this will happen. If this condition fail, then this will happen. So you have to remember this. Then I'll give you an explanation about this example in each and every phase how you are going to do this insertion sort. See, for example, so this is our example. So in this example, the elements of size, see what is the size of array it is. See 1, 2, 3, 4, 5, 6, 7. So now your array size is 7. So n is 7. So what is your index A? It starts from 0 to 6 because it starts from 0 and ends with n minus 1. So 6. So then what is your for loop will say? Now you can start. See, I'll give you the positions of your array also here. This is A of 0, A of 1, and this is A of 2, A of 3, A of 4, A of 5, and then A of 6. See, remember, this is the index. This is the value is available in that particular index. So remember, so positioning is different, value is different. Index always gives you the position. In that index, this is the value. So remember these points before you are going to take an explanation. So now we are going to do pass 1. So now in pass 1, see here we are going through according your algorithm. So we go through an algorithm and then we are trying to understand the things what happens inside. So initially what is your for loop will say? Now your I starts from 1. So now your I equals to 1. So what this will say? So V tends to A of I. So what is A of I is equals to A of 1. Right? So now V tends to, what is your A of 1? It is 45, right? So now your V consisting 45. And what is your J? So J equals to I minus 1. So what is your I? It is 1. So 1 minus 1 is equals to 0. Your J is 0. Then you coming to this step. So while J is greater than or equals to 0. Yes. So this is J is 0. So now the condition is true. And A of J. So what is your A of J? A of 0 is greater than V. So what is your A of 0? It is 89. 89 is greater than, what is V? 45. Right? So 89 is greater than 45. The condition is true. See, while it will take two conditions. The first condition you have to check the index of J. So whether it is 0 or greater than 0. And so now it is a logical operation. So now the both conditions are true, then only you come inside. Otherwise we cannot do anything. Right? Otherwise we cannot do anything. We are exit from the while loop. You just remember this. So now here the condition is true. So what this condition will say? If the condition is true, you can execute these steps. So what these steps? A of J plus 1 tends to A of J. Right? So what is A of J plus 1? J is 0, right? So then J plus 1 is nothing but 1. So what is this 1? It is a position A of 1. Right? Tends to A of, what is your J? It is 0. So what this step will say? You can insert, right, or you can assign A of 1 position with A of 0 position element. So by this, so here in this pass 1 we are considering only these two values. So now A of 1 position is inserted with a value, right, inserted with a value A of J, that is 89. Remember, we are not doing any swapping operation. So just we are inserting the same element into this position. So what about your A of, what about your A of 0 in A of J? It is similar. 89 only is available, right? And after that, you can decrement your J by 1. So now J is decremented, it gets minus 1, right? It gets minus 1 because 0 is there before. So now it is decremented, you get negative value. So now you coming to while loop again. So what it will say? Right? So what it will say? Your J is greater than or equals to 0. Now the condition failed. So once the condition failed, it exits from the while loop and it is trying to execute this statement. So what is this statement? J plus 1. So what is your J now? It is minus 1, right? So now it is getting increment because you can add plus 1. So what is this position? A of 0. So A of 0 position is inserted with V. So what is V? It is 45. So now the 45 is inserted in this position. So now you are getting this is 45 and this is 89. So after this pass 1, so the values are 45, 89, 68, 90, 29, 34 and 17. Right, so this is the value of getting after pass 1. Right, so after pass 1 you are getting the value is like this. So I can write here. So now it is 45, 89, 68, 90, 29, 34 and 17. Okay, so this is your result after pass 1. So now coming to pass 2. Right, so pass 2 you are going to do. Okay, so again we'll go through the algorithm. So now you are exit from your while loop. Again you are entered your for loop. So initially your I value is 1, right? So now when I is 1, now it get increment, you get your I value equals to 2. So whenever your I is 2, your V is contains A of 2 position value. Because A of I, right? So A of 2. So your J will be taken I minus 1. Then 2 minus 1 that equals to 1. Right, so now the positions are same. This is 0 position, this is 1, 2, 3, 4, 5 and 6. So by this second pass you can consider the pass 1 result. Okay, so now what we have to do? So here while j is greater than or equals to 0, say j is 1, 1 is greater than or equals to 0, condition is true. So then A of j, so A of j means A of 1. So this is your A of 1. So 89 is greater than V. So what is V? V is nothing but A of 2 position element, that is 68. So this is your V, right? So now 68. So what this condition will say? 89 is greater than 68. Yes, the condition is true. So once the condition is true, you have to execute this statement. That is A of j plus 1 is going to be inserted with A of j position element. So now here A of j is 1, right? So now j plus 1, that is this position. So now this position is going to be inserted with 89. Remember, this value is never changed because you are not doing swapping. We just insert and this value is also same. And after that your V is consisting same thing only, 68 only. So now your j get decrement, your j is becomes to 0. See, because j is 1 right before, so now it becomes to 0. So it will take 0 is greater than or equals to 0, condition is true. So then A of 0 position. So what is A of 0 position element is 45. So 45 is greater than 68. So now this condition is failed. So once this condition is failed, right? So what we are going to do? A of j plus 1. So what is A of j plus 1? So now this position. A of j plus 1 is nothing but this position. So now this position is going to be inserted with the value V. So what is V? 68. So now this will be 45, 68 and then 89. Okay. Okay. So now in this pass you are getting the result like this. So 90, 29, 34 and 17. So remember, every time, right, we are going to compare the A of ith position element with the remaining elements in the preceding order. Okay, so now I am going to show you the pass 3. So for pass 3, you have to consider this list. So that's in the index is same 0, 1, 2, 3, 4, 5 and 6. So again you come to your for loop. So now your I get increment and your I value is becomes to 3, because in previous iteration it is 2, right? So now it is 3. So this position you have to consider for this next pass. So now from this your list is going to be taken. So now your I is 3, your J is becomes to 2 obviously, because J tends to I minus 1. So what is your V consisting? V consisting A of I, that is A of 3. So V equals to, what is your A of 3? It is 90. Right? So now it is 90. So now coming to while loop, J. So 2 is greater than or equals to 0. Condition is true. And A of J. So what is A of J? A of 2. So A of 2 is nothing but 89. So 89 is greater than 90. So now see, 89 is greater than 90. So the condition is failed. So once the condition is failed, right, so it cannot execute any of these statements. Right, so now you just exit from your while loop. Right, you just exit from your while loop. And this pass, so you have the same order. So simply you can have 45, 68, 89 and 90, and after that you have 29, 34 and 17. So for take the next pass, pass 4. So in pass 4 you have to consider this list. So in this pass 4, now again your I value is get increment. Right, so now your I is becomes to 4 now. See, because this is 0, 1, 2, 3, this is 4. So your I becomes to 4. So when your I is 4, your V consisting A of 4th element, that is 29, right? And your J equals to 3, because 4 minus 1, that is 3. So comes to while loop. So 3 is greater than or equals to 0, condition is true. And A of 3. So what is A of 3? It is 90. 90 is greater than V. So what is V? 29. So once this condition is true, what we have to do? A of J plus 1. J is 3, right? So A of 4th position. So now this position is inserted with a value 90. Remember, this value is also 90. And all the remaining will be same at this pass. Right? At this pass, in this iteration, so this everything is same, only we are inserting the same value into this position. And V is never changed, it is 29 only. Right? So then you have to decrement J by 1. So now J is 3 here. So what is J now? It is 2. So now 2 is greater than 0 as the condition is true, and A of 2. What is A of 2? It is 89, right? So now 89, right? 89 is greater than 29. Because see, this is a condition. A of 2 is greater than B, 29. Yes, the condition is true. Again, what we have to do? A of J plus 1. So J is 2. J plus 1 is 3. So now in this third position, so this 90 is inserted with 89. Right? So because this value is going to be inserted here, this is 89. Remember, this is also having the same value in this iteration. And after that, again your J get decrement. So now your J is becomes to 1. Your J is becomes to 1. Right? So now this 1 is greater than or equals to 0. And A of 1. So what is A of 1? 68. So now 68 is greater than 29. Again the condition is true. So once the condition is true, A of J plus 1 means A of 2 position will be assigned with A of 1 position. So what is A of 1? It is 68. So now this A of 2 position is going to be replaced with A of 1 position. Means inserted with A of 1 position. And after that, again your J get decremented. So now when your J is decremented, you are getting value as 0. So now what is A of 0 position element? It is 45, right? So now the 45 is greater than 29. Yes, this condition is true. So once the condition is true, you have to insert this value to a of j plus 1 position. So what is j plus 1 position? This position. So in this position, you are going to insert value as 45. So remember, this value is same. Now this index is having the same value. And after that, what's happening again? Your j gets decrement. Now we get minus 1. So because 0 minus 1, the value is becomes to minus 1, right? So now it becomes to minus 1. So once it is minus 1, so this condition is failed. So you exit from while loop and you are going to execute this statement. So what this statement will say? J plus 1. So what is your j plus 1? So j is minus 1. J plus 1 is 0 position. So now you are going to insert a of 0 position value with v. So now this 0 position value is going to be inserted with 29. So you can keep the remaining elements are same, that is 34 and 17, right? So now we are going to do the next pass. Okay, so that is pass 5. So here I am doing pass 5. So in this pass 5, remember this is 0, 1, 2, 3 and 4. Now we are going to consider this position. This is 5. Because your for loop will say your I is becomes to 5 and v equals to a of I. So that is 34. Okay, a of I means a of fifth position element is 34, right? And then your j is 4 because it is I minus 1. So 4 is greater than or equals to 0 condition is true, and a of j means a of fourth position, that is 90. So 90 is greater than v. So what is v? V is 34. Yes, the condition is true. So then what's happening? So now you have to insert a of j plus 1 means a of fifth position is going to be inserted with the a of fourth position element. So after this you are getting like this. See, I can write the same order so that I'll show you the replacement things. 89, 90, 34 and 17. So now you are going to operate at this point, right? So we are at this point. So now this is your I and this is your j. Okay. So now this position is going to be inserted with 90. And you can remember all these position elements are similar. And then you are going to decrement your j. So now you are getting this position because initially your j is here, right? So now here you have. So 89 is greater than 34. The condition is true again. So what's happening? Now this position is inserted with 89. Again your j get decrement and you are getting this position. So 68 is greater than 34. The condition is true. Again this 68 is inserted in this position. So now j get decrement, you are getting this position 45. So 45 is greater than 34. Again the condition is true. So that this position is going to be inserted with 45. And then again your j get decrement and now you are getting this position. So at this position, so 29 is greater than 34. So what's happening? This condition is become fail. So once this becomes fail, right? So you are not going to insert 29 into this position. Simply what we are going to do, so we have to decrement the value of j. So that is you are at this position only, right? So simply we are going to place means after you are getting decrement, so you are getting this value 29. Now you are at this position, right? So now it is j plus 1 position is this position. So in this position you are going to insert v. So what is this v? 34. So now you are going to insert 34 here and 29 is in this position only because here the condition failed. So and the remaining the value is same in your pass 5. So now coming to pass 6, so which is your last iteration. So pass 6. So for pass 6 you have to take the result of your pass 5 and here you get I value is get increment. Now I is becomes to 6. right? So your I is becomes to 6. So I equals to 6 and V equals to A of I, that equals to 17. A of 6 equals to 17 and J equals to 5. So now you can take this element and you are going to compare with all the remaining elements to make this 17 into the correct position. So before that also you can identify that 17 can be placed here and all the remaining elements needs to be moved one position back. Right? So now see how it can happen in past 6. So now here J is 5 is greater than or equals to 0 condition is true and A of 5 is 90. So 90 is greater than 17, the condition is true. So then what's happening? So now you are getting 90 into this position because J plus 1 position you have to insert A of J. So 90 is here. So now you can decrement your J, you are getting this position. So 89 is compared with 17. Again the condition is true. So 89 is inserted in this position. Now 89 is coming to this position. So now J get decrement, you are getting this position. So 68 is greater than 17. So now the 68 is inserted into this position. So after that J get decrement, you are getting this position. 45 is greater than 17. So again the condition is true. So 45 is inserted in this position. And after that J get decrement, you are getting 34. 34 is greater than 17. The condition is true again. So that again you are inserting this position, that is 34. And then J get decrement, you are getting this value as 29. So 29 is also greater than to 17. So that this value is inserted in this position. Now it is 29. So you can find out that A of 0 position value is there and this is 29 itself it is having. And after that J get decrement, you are getting J value as minus 1. So once it is minus 1, this while loop will get exit because it takes the values from 0 to more than that. So this condition failed. So then what's happening? So J plus 1 position you have to insert the value of V. So what is J plus 1? So here J is minus 1. So now you can add. You are getting a position J equals to 0. So at A of 0th position, you are going to insert your V. So what is V? 17. So now for that, it will insert 17 into this position. So after the 6th pass, you have identified that all the elements in a ascending order. Okay. And then you can increment your I by 1. So now you are getting 7. So 7 is greater than 6. The condition failed. So that your for loop is also, it gets to be exited. So in this way, you can use this algorithm to sort the list of elements into insertion sort. I hope you all can understand this algorithm and the example program. So if you have any doubts, you just ping me in comment section so that I'll clarify your doubt. Thank you so much. Hi everyone. In this video, I'm going to explain depth first search in design analysis of algorithms. So depth first search. Here I discussed about this topic in design analysis of algorithms under decrease and conquer method. Right, so this is an algorithm. So first of all, we try to understand this algorithm. So then we can solve this particular problem. Okay. So now this is an algorithm for DFS. So now we have to take one graph. So this is a forest actually. So see, you can observe that there is two graphs. So now there is no connection between this graph and this graph, right? So such type of graphs is said to be a forest actually. So now we can apply this DFS algorithm on this graph a little bit later. So before that you are going to understand this DFS algorithm first. So then we can solve this problem. So now in depth first search we can apply on this graph. So these are the comments. So that implements a depth first search traversal of a given graph. So input is a graph which consisting the vertices and edges. So capital B. So capital V is nothing but set of all your vertices. Capital E is all of your edges, right? So these are all vertices like A, B, C, D, E, F, and G, H, I, J. So these all are the vertices which comes under this capital V. So whereas capital E, all the edges. So here you can observe that this is an unweighted graph. So there is no weights on edges. So because of that, it is said to be unweighted graph. So now what will be your output? So now your graph G with its vertices marked with consecutive integers. So in the order they have been first encountered by the Bfs graph. So now this order will gives you like in which order you are going to travel your DFS of this particular graph. So that is given by an integer values here. Okay. So now you can start the algorithm. So see here. So this is means you can mark each vertex in B with 0 as a mark of being unvisited. So now you can take the set of capital V, so which consisting all the vertices like A, B, C, D, E, F, G, H, I, and J. So all these vertices is a set of V. So now you mark all the vertices of V with 0. So now initially all are zeros. So A 0, B 0 and C, because all the vertices are unvisited at this state. So now you can initialize your count with 0. So now you can start the count, because we are every time we are incrementing this count value and we are assigned to this vertices, which gives an order of we are inserting an elements into your stack, and order which you are popping from the stack. Right. So before that we have to remember Bfs algorithm is used to implement by using stack. So stack is nothing but it's a data structure. So where the insertions and the deletions can be taken at the single place. So which is said to be a top of the stack. So this is also said to be a LIFO, because the last inserted element is to be deleted first, right? So it will follow the LIFO fashion. So now you can initially you can initialize your count variable with 0. So what we can do now, so for each vertex V in capital V, so these are all the vertices. So these can be represented with small v, right? So now for a capital V, do. If V is marked with 0, so see if any of the V is marked with 0 is nothing but the vertex is not visited as of now, right? So then you can apply DFS of V. So for that vertex you can apply the DFS algorithm, right? So now what is your DFS of vertices will say? So see, visit recursively all the unvisited vertices connected to the vertex V by a path, and number them in the order they are encountered. So via a global variable counter. So here once you visit that particular vertex, you have to increment the counter value. So and that count value you can assign to that particular vertex V. So for each vertex W in V adjacent to V. So what is the meaning of that? So for every vertex some other vertices are connected. So those vertices are said to be an adjacent vertex to the current vertex which you are going to see. So now you can take that adjacent vertices and you can see if W is marked with 0. So what do you mean by if any vertex is marked with 0? That indicates that that vertex is not visited. So now you can apply for that adjacent vertex to again DFS. So what your DFS will say? So you can take the vertex again and you are trying to find the adjacent vertex to that, and you can identify that if any one of the vertex is not visited yet, then you are trying to visit that vertex and you make the count is to be incremented, and you can assign that incremented value to that particular vertex. So this is an algorithm. So now I'll show you. So how you can solve this particular graph, means how you can apply this DFS algorithm for this graph, right? So I'll start with the vertex A. Right, see here. So now what this A, B and C will indicate is, see in this example DFS travel, A is a graph. So this is nothing but your graph, right? And then you can see here B is nothing but traversal stack. So now this is the content of your stack. So here you can observe that there will be two values. So here the first value which indicates that the order in which the vertex was visited. Means suppose if this vertex C you have the value as 3, that is nothing but at third time you can visit this D. Right? Means you are first visited A, then C, then D, like that. And the second value means see here, it will gives you the popping position from the stack, right? See, second one indicates the order in which it became a dead end. So that is popped off the stack. So and whereas this C, it is a forest, Bfs forest. So with the tree edges shown with a solid lines and back edges will shown in a dashed lines. Right? So I'll explain you about this a little bit later. We just go through that. So now we can start with the vertex A. So I'll start with the vertex A. So now I'll mark it. So initially this vertex is marked with 0 because this is unvisited end. So now, so I can increment my count value by 1 because I just visited this vertex A. So now the count value is 1. Right? See here, you can observe that the count value is 1, right? So now I'm trying to find what are the unvisited vertices with this particular vertex. So now I'm finding of that I have 3 vertices from A. So one is C, another one is D, another one is E. Right? So now these are the 3 vertices adjacent to my vertex A. Right? So now I'm trying to take this adjacent vertex, again I can apply DFS. So what your DFS will say, again I need to find what are the unvisited vertex from C. So now see, you just increment this value. So here it has become, so initially the count value is 2, right? So now it becomes 2. Because I need to increment the count value for this. So now it is 2. And so from this C, I'm trying to see for this, these two are unvisited because from A I'm trying to visit this particular node first. So the count value is 2. So now from this C, I'm trying to visit all the remaining unvisited vertices which is connected to C, that is D and F. So now from C, I have D and then F. So now I can increment D by 1. So now the value is 3 here because after C I am going to visit my another vertex D. So now that count is 3. And from that D, I am going to visit the unvisited vertices. See, this is your D, right? So now these are 2 adjacent vertices A and C. Now you are finding of that A and C is already visited. A and C is already visited. See, because A value is not 0 and C value is also not 0. So then this is said to be dead end. So this is said to be dead end because I didn't have any other possibility to move from D. So this is my first dead end, right? You just remember. So now I can give this dead end positions after this I'm visiting all the vertices. So now see, so the next one is F. So now I'm coming here. So I can increment my counter value. So now this will becomes to 4. So after this F, I'm going to see the another unvisited vertices. So I'm finding 2 vertices. So one is B and another one is E. So from these 2 unvisited vertices, I'm trying to see my first vertex as B. So I just increment my count value. So now it becomes 5. Right? Now it becomes 5. So now I can see that from that 5, so from that B, I have one more vertices which is adjacent to that. So that is E. So now E is unvisited. So that from B I am trying to take this E value. Right. So from that I am trying to take this value E. So now you can remove these 2 because you are not taken this value from A. So from C you are taken B. So like that. So that I just remove this edges. So now B is assigned with 5 and E is assigned with 6. So now you can observe these suffixes. See, I am first visited A and then I visited C and then I visited D and then I visited F and then I visited B and then E. So see, 1, 2, 3, 4, 5 and 6. So which vertex is going to be become a first dead end, this one. So now I just remove D first. And after that I can find out that this is a dead end, because from this I didn't take any of vertices to reach. So now this will be a second dead end. And now and after that I can see this is my third dead end. Right? And after that, so your F is becomes to the fourth dead end. And then your C will be fifth dead end. And A will be the sixth dead end. So because of that, it will given you the suffixes values like this. See, A, 1, 6. Now you are finding 1 and 6. So this is the order which you are going to push into stack. And this is the order which you are going to pop from the stack. So now you are popping D first, and then E, and then B, and then F, and then C, and then A. So now tell me the order. So now you can take D first, and then E, and then B, and then F, and C, and A. So for this internal graph, you are getting the order like this, right? And then now I am showing the external graph. So from this external graph, so I am started from vertex G. You can apply the same thing, right? So now you can start from Z. So from that Z, because initially G, H, I, J all are having zeros only, because all the vertices are unvisited. So now, so I can start from Z. So I can find out that here two unvisited but adjacent vertices. So now that is H and J. So I can take this one first. So see here, you just remember your counter value is 6 here. As on completion of your internal graph, your counter is 6. So now your G becomes the counter value is 7. So which is inserted the order into your stack. So and then this value is 8. Because after G I am going to visit H. Right? And after that, from that H, I am going to see the another adjacent vertex, that is I. So now this is I, right? So the counter of this is 9. So now it becomes dead end actually. See here, the order is given G is 7 first, and then H is 9, and then I is, sorry, H is 8 and I is 9, right? So and then this is, you just backtrack and you are getting, see, this will be dead first. So now you can take, this is 7, because here the dead end is 6, right? So now this is 7, and after that, this dead end is 8, and this is not a dead end. See, because, see here, this will be, we can travel from G. So from G, you can view the another unvisited vertex G, J. So now this value counter, it gets 10. And now this will be the dead end. So this value of dead end is 9. And this is 10. So now you are getting, so this will be your first dead end. So because, so which node is said to be dead end? From that node, you are not visiting any other nodes. Means from that node, you are finding all the adjacent vertices are already visited. So such type of vertex is said to be a dead node. Okay. So now here, so this is an order we are popping. Means tell me in which order you are going to pop now. So now after A, so this is I, and then H, and then J, and then G. So now this is your DFS order according to this algorithm, right? According to this algorithm, so this will be your DFS order, right? So I cannot say like every time you are getting the same order, because from A, here I am traveling C. So because of this I am getting this order. Suppose from A, if you are going to travel D, then you are getting the another order. Or else from A, you are trying to visit E first, then you are getting the another order. So for BFS or DFS, you just remember, so one order is not your solution. So you can have any order, depends on that in which order you are going to visit all the vertices which is connected to your current vertex. Okay, so this is a depth first search using your decrease and conquer method. I hope you all can understand. Thank you. Hi everyone, in this video I am going to explain breadth first search. Right, breadth first search in design analysis of algorithms. So by using decrease and conquer method. Right, so in this method how you are going to solve your graph traversal technique, that is of your BFS. Right, BFS. So before I'm going to explain the example how we are going to solve, we will see an algorithm. First try to understand this. So BFS algorithm will take your graph as an input. See, these are the comments. So implement depth first search traversal of a given graph. Your input is a graph which consisting vertices and edges, and your output is a graph G which its vertices are marked with the consecutive indices in order they have been visited by the BFS traveler. So remember, breadth first search can be implemented using a data structure called queue. So queue is a data structure where the insertion and deletion can be taken in two places. So one is front, another one is called rear. So always the values it should be inserted at the other end called as a rear, whereas the element is to be deleted from the front end. Right? See, for example, if you take this as queue, so this is said to be front and this is said to be rear. Right? So now you can done the operation on queue on both ends. So everyone it can be added from the back and everyone can be removed from the front. So you have to remember this structure in your mind. So now, so mark each vertex in V with 0 as a mark of being unvisited. So at the initial stage, so you didn't visit any of the vertex from this graph. So you can take every vertex as value 0. See, initially we have so many vertices like A, B, C, D, E, F, G, H, I, and J. So all these vertices are unvisited, so that every vertex is having a value 0. So A 0 and so on. At last value you can take as J is also 0. So this is our initial position, right? So this is an initial position. So now count, you can take one global variable, that is count, which you can initialize with 0. So for each vertex V in capital V. So capital V is nothing but set of all your vertices. So what are all the vertices you have? A, B, C, D. All these vertices are said to be small v, right? So E, F, G, H, I, and J, right? So these are said to be small v. So now all the vertices in capital V with 0. So what indication of that means every vertex is not visited. So what we can do, if V is marked with 0, then you can apply BFS of V. So BFS of V is nothing but you can apply the breadth first search for that vertex. So what BFS will say? See, visit all the unvisited vertices connected to the vertex V by a path and assign them the number in which order they are visited via the global variable count, that is a counter variable. So once you start visiting a particular vertex, you can make it as a count 1. So once you start the visiting of the second vertex, you can increment your count value by 1, and so that you are getting the value as 2 for B, and so on you can do. See, mark V with a count and initialize a queue with V. So see, initially your queue is empty, so nothing is there. So for see, while the queue is not empty, so you can do the same thing, means you can add something to your queue and you are trying to delete the things from the queue. So you can do until you're finding your queue is empty. Like see, if your queue is not empty, so for each vertex W is nothing but an adjacent vertex. Suppose if I taken A as my vertex V, so then all the adjacent vertices like E, C and D is said to be adjacent vertices, which is indicated with W. W in V adjacent to the front vertex. So what are the first vertex you have? Now you can take the adjacent vertices of all the adjacent vertices and you can place into your queue. See, count, it can be incremented, mark W with a count and add W to the queue. So now that unvisited vertex you can make it as a visit and you can put into your queue. So remove the front vertex from the queue. So after your placing the adjacent vertices into your queue, then you can remove the current vertex which you are going to be visited, right? So I'll explain this example. So this is a graph, right? So now we can solve this graph by using breadth first search. So this is a forest actually, because we have the collection of two graphs here. So now see here I'm started with vertex A. So this is my internal graph. So I can start with my vertex A. So now this is my queue, right? This is my queue. So initially my queue is empty, right? So this will be my front and this will be my rear also, because I didn't have anything. So now my front and rear both are same. Here in this initial situation, your front equals to rear. So now you're going to insert A here. So see, A will be the first one. So now you have three vertices which are connected to this A. So what is that order? C, D and E. See here I am taken alphabetical order, right? You can take any order like D, C, E, or else you can take E, D, C, or else you can take C, E, D, any order you can take. So here I am taken in ascending order like C, D, and after that I will take E. So now I can add all these unvisited vertices. So I can give I can give my count value. So initially A is 1, now C is becomes to 2, and D is becomes 3, and E is becomes 4. So now I can add these things. So C, D and E into my queue, and then see what it will say. Remove the front vertex from the queue. So now just I remove A from the queue. So and I am placing in my BFS order. So now my order A will come first, because see your queue will follows always, the data structure will follows the fashion FIFO. So FIFO, first in first out. So in order which is inserted into your queue first, and that will be the element which is deleted from the queue is also first. So now you coming at this position C. So for this C, now you are trying to find all your unvisited vertices. Now see, for C, the adjacent vertices are D and F. Now you are finding D is already visited, because D count is 3, it's not 0. So that is visited. So when D is visited, you are going to see the unvisited vertex from C, that is F. So now you just insert into F and give the F into the counter value. So now you just remove C, because from C you reach all the vertices which are adjacent to that. So now you just remove C and you can place into your BFS order. So this is your BFS order. So now you can remove C. So I just remove C from my queue. So now my next vertex is D. So now for this D, I am trying to see all the unvisited vertices. So now for D, see I didn't find any unvisited vertex, because A is having some value and C is also having some value. So now this is my dead end. So I just remove this. I don't insert anything into my queue, because I didn't have any unvisited vertex from this D. Okay, and after that, so now you can move to the next element in your queue, that is E. So now for that E, I am trying to visit all my unvisited vertices, that is F and B. And you are finding that F is already visited, right? So F is already visited, because of that it is assigned with 5 and it is placed in your queue. So which one is unvisited from E? So B is only the unvisited. So now you can insert into your queue and you are assigning value as 6. Okay, and you just remove, don't forget these two steps, you just remove E from the queue. So now E is here, right? E is here. So now next one is F, and you are finding from F, it didn't have any another vertices to unvisit, right? So all the vertices are visited. So you just remove from the queue. So F is visited, so that it can be removed from the queue and it will be placed in your BFS order. And after that it takes B. And from this B also you are visiting all the vertices, so there is no unvisited vertex, so you just remove from the queue and you can place it into your BFS order. So now see, you're finding this order 1, 2, 3, 4, 5 and 6. And now you're getting to external graph. So now see here, the external graph, I start from G, right? So from that Z, see, I can place into my Q. See here, I started from G, so the value for G is 7, means the counter value for this G is 7. Okay, so then I'm trying to visit all the unvisited vertex from G. So I have two vertices, one is H and second one is J. So from these two, I'm taken again in alphabetical order. So H I'll take first, right? So from that I can insert H and then I can insert J, right? So now I just remove G from the Q. And remember, you can assign values for Hn, right? You can assign values for H and J. So H is 8 and J is 9. So you can remove G from the Q. So now you can place it into your BFS order. So this is G, right? And then it is come with H. So from that H, I am trying to see all the unvisited vertices. So from H, I have only I is unvisited. So I just uh, insert into my Q and I can give value of I is 10, right? So I just remove H from the Q. So now H is removed from the Q and it will be placed in your BFS order, right? And after that, so you are taking the next value as J. From that J, I am trying to visit all the unvisited vertices, but here there is no unvisited vertex because one vertex is adjacent, but that is already visited from H. So now I just remove this J from Q. So simply I can add this J to my order. And after that I have only one element. So from that also I didn't have any other unvisited vertices. So simply I just remove from the queue and I can place it in my BFS search. So now you can see the order A, C, D, E, F, B, G, H, J and I. So this is my order of BFS. So remember, so not only this is your order, right? You can take, see here I am following the alphabetical order. For that I am getting this order. Right? If you are going to travel with any other order, like from A you are going to travel D first, then you are getting your order is different. Right? For everything it is correct. Right? So for that BFS and DFS, you just remember everyone you are didn't get the same order. Right? But you have to follow the algorithm and you have to solve your problem. I hope you all can understand. And see, this is the way how you are going to visit your vertices. From A, I am going to visit C, D and E. So from that D, I can reach C. From that C, I can reach F. Right? From that E, I can reach B. See here in this way means the dark lines that will show you like you are going to travel from here to here. The dotted lines is also gives you the information there will be a possibility. See from A, you can find out that A, C, D, you can find out. See this is the order you have. So that will be defined by this dotted order. Okay. So thank you. Hi everyone, in this video I am going to explain the concept of topological sorting in design analysis of algorithms under decrease and conquer technique. So before I am going to explain the different ways how you can solve your topological sort in design analysis of algorithms. So I'll give you a definition of topological sorting. So topological sorting for any directed acyclic graph. So directed acyclic graph is nothing but a directed graph which consisting of a cycle. See for example this graph. So now you can observe that each and every edge is having some direction and this graph will consisting the cycle. So this type of graph is said to be a directed acyclic graph. So by using this graph you have to find the topological sort, right? So remember we cannot find we cannot doing the topological sorting for any uh, graph which doesn't consisting of the cycles.
So now topological sorting for any directed acyclic graph is a linear ordering of vertices. That is nothing but you can arrange all your vertices in some order such that for every directed edge. So directed edge is nothing but like this. So now you have an edge which having some direction. So either incoming or outgoing, any of the direction it's have. So now this edge can be connected to vertices u and v. So remember always u comes first before v. So in your ordering, so always remember vertex u comes before v in the ordering. So that is said to be a topological sorting. So in design analysis of algorithms, we are using two types of algorithm for solve this problem. So one is a directed, depth first search algorithm, and the second one is a source removal algorithm. So now I'll explain each and every method how you can arrange these directed acyclic graphs to topological sorting order. So in my previous video, I already explained the depth first search algorithm with some example. So we'll just go through that so that you can understand in a better way, right? So here, so what your depth first algorithm will say is, you can take all the vertices of your graph and you can assign with initially with a 0. That indicates that all these vertices are not yet visited. So you can start with any of the vertex from your graph, right? See here, for example. So I started here from vertex C1, right? So here I started from a vertex C1. So initially my value for this is 0. So I can take one counter variable. So I can increment that and I'll assign 1 to this C1 because now I'm visiting this vertex. So from that I'm finding the outgoing edges of C1. So now I'm getting only C3. So which I can reach from C1. Right? C3 I can reach from C1. Right? Because I have a outgoing edge. Right? So now I didn't have any other adjacent vertices. So from C1 you can see the unvisited vertex C3 which is an adjacent to this vertex C1. So now for C3 you can give the count as 2. So from C3 you can have an adjacent vertices C4 and C5. So you can visit C4. So because this will come before this, so I'll give the code as 3 for this, means the count value as 3, and then I can find from C4. So I can reach C5. See, from C4 I can reach C5. So I can take C5 from C4, right? So simply I can remove from here and I can give the count as 4 here. So from C5, so cannot have any adjacent vertices for C5, and so this is a dead end, right? So you can take this is your dead end. Okay, and then from C4 again I am trying only C5. C5 is already visited, so now C3 is also a dead end. So C4 is also a dead end. So for C3 again I am finding C4 and C5 is already visited. So C3 is a dead end. From C1 also I didn't have anything. So C1 is also a dead end. And you are finding that another vertex C2 which is not yet visited, so that you can take C2 and you can give the count as 5. Right, see here. So now you want to remove. So this is one dead end because it doesn't have anything. So that will be removed first. And then C4 is removed. And then see the order is given, right? So see here C5 is the first dead end. So you can remove this one first. And then you can remove C4. This is your second dead end. And then you can remove C3, this is your third dead end, and then you can remove C1, this is your fourth dead end, and then this is your last dead end, that is 5. So now the order is given like this. So you can remove C5 first, and then C4, and then C3, and then C1, and then C2. So this is a topological ordering. So now you can popping off this order, right? See C5, C4, C3, C1, C2. So now you can give a topological sorting list for this is, see, you can take C1 to C3, right? So you can move from C1 to C3. From C3 to C4 you are moving, right? C3 to C4. From C4 to C5 you are moving. So now you can place C2 separately because this is not yet connected to anyone. But you can observe that C2 can be visited before C3. Right? See what this graph will say. Now you have an edge from C2 to C3. So now you have to place C2 before C3. So now you can take like this. And you can find out that for C3 also we have two, that is C4 and C5. So before C4 and C5 you must have C3. So now you can observe this for C4 and C5 you have C3 first, right? So from C3 to C4 you have directed edge and then this one. So this is a topological sorting by using a DFS algorithm. So whereas the second algorithm is source removal algorithm. So for this source removal algorithm, so this is a direct implementation of the decrease and conquer method. So now these are the steps we can follow in this source removal algorithm. So from a given graph, find a vertex with no incoming edge. That is nothing but the vertex which is having the outgoing edges. So now delete among with all the edges outgoing from it. If there are more than one such vertex, means if you are finding more than one such type of vertices, then you are going to choose randomly and you can remove like that. I know that vertices that are deleted. So all the vertices which you are deleted, you can take that order and you have to note aside. And all these recorded vertices will gives you a topological ordering. So this is your graph, right? So now you are finding here C1, C2, right? C1, C2. So now C1. So what your first step will say, which having no incoming edges. Now you are finding C1, C2 is having no incoming edges. It's having outgoing edges. So you can choose either C1 or you can choose either C2. So I'm choosing C1 here. So from C1 I just remove this C1. So now I can remove the edge also. So now you are getting this graph. So again you are finding C2 is having the same way, so that you are removing C2. So that you can remove all the edges which is connected from C2. So now you are getting this graph. So now you are finding C3 is doesn't having any incoming edges, right? So now you just remove C3. So now you are getting this path. So now C4 is not getting any incoming. See, C5 is having incoming, like C4 is not having. So just remove C4 and then C5. So which order it will gives you? Here you are deleting C1 and here you are deleting C2 and after that C3 and C4 and C5. So now the order is C1, C2, C3, C4 and C5. And you have to find out the topological sorting constraint. So you have to visit C4 and C5, right? Before that you have to visit C3. See here. So this is a topological sorting and design analysis of algorithm. So I hope you